Good morning to everyone. On behalf of the Universidad de las Américas and Ensure 6G Consortium, it is a great pleasure to welcome to you the first day of our training module titled Advanced Wireless Network Security and Privacy. This is part of the Horizon Europe Marie Curie Staff Exchange Project Ensure 6G. As a mobile networks evolve toward their 6G generation, we are entering a new technological era where ultra-connectivity, automation, and data-intensive applications will transform sectors such as healthcare, transportation, and energy. However, this transformation brings with it a profound challenge regarding security, trust, and the protection of privacy. Ensure 6G is a visionary project that seeks to address these challenges by combining interdisciplinary expertise from 15 partners across Europe, Asia, and Latin America. Through collaboration between academic and industrial partners, the project focuses on developing innovative, trustworthy, and human-centric security and privacy solutions for V5G and 6G network. One of Ensure 6G key pillars is training the next generation of researchers and professionals with a deep understanding of technical, legal, ethical, and social dimension of future communication system. This event is part of that mission. We are thrilled to begin with a highly relevant and foundational topic, that is security mechanism in 5G and 6G. In this day, for our first talk is with the Professor Anne Braeken, that is the University of Brussels. This with the topic is basic mechanism of security in 5G, 6G. I will introduce to her, welcome Anne. We will introduce Anne Braeken received the master degree in mathematics from Ghent University in 2002 and the PhD degree in engineering science from the research group COSIC EQU in 2006. She became a professor in 2007 at the Erasmus School, Brussels, since 2013, University of Brussels, Department of Engineering Technology. She is also the academic responsible for the postgraduate program on digital essentials and skills. Her interests include security and privacy protocols for the IoT, cloud, and fog, with a current focus on blockchain and 5G, 6G security. She has developed several lightweight security solutions for different application domains, like healthcare, transportation, home automation, etc. She is a co-author of over 200 publications. She has been a member of the program committee of numerous conferences and workshops and a member of the editorial board for several journals. Since 2015, she has been an evaluator for several Europe proposals and ongoing projects submitted under the program of Horizon 2020. Marie Curie and ITN. She has cooperated and coordinated more than 20 national and international projects. She has been ranked among the top 2% researchers in the world by Stanford Elsevier top 2% ranking 2021-2023. Yeah. Welcome to Anne, and you can start with your presentation and with his topic, the basic mechanism of security in 5G, 6G. Welcome, Anne.
Thank you, Paola, for the introduction, I would say good morning for you over there. It's already evening or almost evening here in Belgium. So I'm gonna see if I can upload my presentation. Let's see. That works. Okay, do you see my slides?
See,
we see
it's
that.
okay. We can see yours.
Okay, good. So we were supposed to start in 8 minutes. Do I already start or do I wait? I'm not sure if others are still going to come or not.
See, it's okay. You can start because now the audience is there, and we start a little bit before because for some proofs, but now the people is here for your
Okay, you're all
presentation. Thank you.
following. You're
Maybe
all
if I can
following. Oh, sorry,
So
please.
sorry.
Maybe if I can just jump in. There are, hi Anne, it's Bart here. There will be also time for questions, so we have allocated enough time. Maybe I would suggest at the end of each presentation, because we have some. It's a hybrid event, so we have quite a lot of people online, and I can see they are still joining. I will be monitoring also the YouTube channel in case there are any questions there. And also, I think we have some students and staff in person in UDLA. So perhaps Paola, you can monitor on this side if there's any human in person questions. You can take them, and we can take a look at the chat. And at the end of each presentation, we can ask the presenters if there's anything coming up. So yeah, that's just my 2 cents here in terms of organization of the event.
Okay, so we
Thank
keep
you.
the questions for the end.
Yes.
See? Yeah.
Okay. Okay, good. So then I suppose I start. So I think everything regarding the introduction has been already said. So I just want to add that if you have questions regarding this talk or other things related to this talk, don't hesitate to contact me. So you can find here the email address on the site. Okay, good. So for the talk of today, so I will start with some history. Then I shortly explain the 5G specific architecture, security threats related to this architecture, and finally I will end with some conclusions, key takeaways. So we'll start with a bit of history. Before we come to the 6th generation, there have been several generations past. So the capabilities in each of these generations, they drastically increased. But not only the capabilities, because as you can see here on the slide, also the different types of attackers and the capabilities of these attackers also increased over time. And now what we are going to do is quickly go over each of these different generations and let's discuss them a bit more with a focus on security related aspects. So we start with the 1st generation, and the 1st generation of cellular systems were limited to voice services, analog, and which was analog communication. So, and with respect to security, there was in fact totally no explicit security measures taken into account because of 2 reasons mainly. First, it was not so easy to do on analog communication. And secondly, security was not at all popular outside the military world. And we are speaking here the 70s, 80s. And so as a consequence, all communication was open. And so all types of attacks going from eavesdropping, data privacy breaches, authentication issues, everything that you can imagine was possible. So it must have been a dream for hackers during that time. But luckily, they were not so active then. And then 10 years more or less later, we are in the 90s and we have the 2nd generation that was developed. And now, for the first time, it was not anymore analog communication, but it was digital communication. It's called now the GSM, or the Global System for Mobile Communication, and that became the most widespread use standard. Regarding security, there were 4 priorities. So anonymity, authentication protection, senior protection, and user data protection. And unfortunately, besides these 4 priorities, which were more or less established, there were still several issues. So first of all, the network operator was not able to do the verification of was able to do the verification of the authentication, but not the other way around. So it was completely possible that there was a fake operator because the user was not able to authenticate or to verify that. So we had only unilateral authentication. Man-in-the-middle attacks were perfectly possible. The whole system was also built, there were the 90s, on the principle of security by obscurity, meaning that the details of the security mechanisms that were inherently used, because in order to have user data protection, there were encryption mechanisms used, but the details of these algorithms, they were not published, and so they had to be revealed by means of reverse engineering. The drawback is it takes a bit more time, but it was feasible, and the community were able to derive the cryptographic algorithms, and they were called A51 and RC4, and both of them were very badly broken. So although user data protection was established, it wasn't really established because the underlying cryptographic mechanisms were very weak. And then the third thing or the third disadvantage of issue was that tracking was possible. So the privacy of the identity was only protected by means of a pseudonym. And this pseudonym was fixed for each particular user during the whole lifetime of the device. So if you were at some moment possible to make the link between a pseudonym and the real identity, which you might maybe do in case of a very important person, then you can completely track the whole behavior of that person. And then, of course, we also have the denial of service attacks. And actually, that's an issue that you will see in each and every generation. It becomes a bit more difficult, but it's not something that you can solve only by means of cryptographic operations. So, and then, the last main issue was that everything was fixed. So all security that was used in it, all the different algorithms, implementation, protocols, everything was fixed. So it was not possible to upgrade it at a later moment. So that was the second generation. Then we come around 2000, so the third generation that was on the market. We had at that time higher data rates than 2G, limited video streaming, also video calls became possible, and there was a huge improvement in data rate compared to 2G, which clearly nothing of video was possible. From a security point of view, important to mention is that in 3G, now we speak about the so-called ACA protocol. It's called the Authentication and Key Agreement Protocol. It's the same mechanism that we had in 2G with some improvements on top of it, but now it got a formal name of an ACA protocol. So, like I said, structure-wise, it was similar, but it's a bit stronger. So what we have, for instance, is that we have still this anonymity track, but only anonymity. So they use the pseudonyms, but they were just a little bit more frequently updated. So it's still limited, so the traceability attacks are still there. Then there are still issues with weak encryption algorithms, although the previous ones, A51, that was replaced by Kasumi, that also turned out to be weak. And so then what we also have was denial of service, of course, is that the cloning of SIM cards was a big issue at that time. And that followed from the fact that the physical security protection of the data, which would which should be stored in tamper-proof memory, was not strong enough. So key and identity data could be easily retrieved from the card and then stored in another card in order to, in fact, impersonate the user. Okay, good. Then we go to the fourth generation. So in 2010, it's in fact what we have actually still today in some of the cases, it's 4G or LTE, long-term evolution advanced network, in which video streaming, video calls become much more feasible, and we have a very huge improvement in data rates. So the fourth generation supports also the third generation partnership project, 3GPP, which is a collaboration between telecommunication standards organizations that communication standards organizations that develop protocols and specifications for mobile telecommunication systems. So overall, while 4G is not directly linked or based on 3G technology, they inherit and extend the access security mechanisms that were defined by 3GPP. It's also important to know that this technology of 4G is interoperable and backward compatible with 3G. Now, regarding security innovations, one of them is the introduction of a new ACA, Authentication and Key Agreement Protocol, which is also the one that come later to it, similar in 5G, but some small little things, changes made. So important to mention is that it also supports the non-3GPP technologies such as Wi-Fi, Bluetooth, and other local area network and personal area network technologies that can communicate with 4G networks through specific mechanisms and interfaces. And furthermore, important security feature is that for the first time, there is a cryptographic network separator such that the spreading of attacks can be limited. And so it basically means that the user equipment can authenticate to the serving network, the roaming in fact, and that is based on the approval of the home network. So serving network is really completely different, physically different from the home network, while before it was like one integrated part. Still, we have denial and distributed denial of service attacks, and then there are also issues with the ACA protocol, but I will come to that later on. Good, and then around 2010, it's the great breakthrough of the IoT, Internet of Things. These are the small constrained devices that are connected to the internet. And there were many advanced developments in different domains, and going from sensors to applications. And also it resulted, in fact, into additional challenges for the communication network to be able to support them. And that's also one of the reasons, in fact, that we come into the 5G era, which we have today at 2020. And that's it's not like just a simple incremental improvement, like with 3G versus 4G. In 5G, we have drastic change. And if you can see here the different features on this figure, there is a drastic, so 4G is the dark blue, and then the light blue is here the 5G. Then you can see that there are drastic improvements with each of these different features. So, and there is a huge market also around this 5G, which makes it very attractive. I know the project is about 6G, but in fact, we are still, or at least in Europe, still in the phase of rolling out 5G, which is not at its optimal usage of capabilities. So it's still important to also talk about 5G. And in addition, many of the things that will be used in 6G will build on top of 5G. And we will look at the different issues that are still present here in 5G and not solved in, hopefully will be solved then in the 6th generation. Okay, now we will delve a bit more into the 5G specific architecture before we can actually speak about the security threats. So as you can see, we have these drastic improvements with respect to data rate, bandwidth, etc. But then the question is how to obtain that. And there are different reasons. So first of all, there are quite some reasons that are related to improvements with respect to radio communication. So first thing is here new spectrum, as 5G utilizes a broader range of frequency bands, including higher frequency bands like millimeter waves, and they offer wider bandwidths, enable faster data rates, and support the deployment of new services. And then the second thing is that there were also advancements with respect to antenna technologies that include beamforming and massive MIMO, multiple inputs, multiple outputs. And it's this beamforming that allows for more focused and efficient signal transmission, while the massive MIMO improves the overall network capacity and coverage. The third improvement is related to a flexible frame design that allows to adapt and configure the structure of communication frames based on specific requirements of different services and use cases. So examples of this is that you can have a variable slot duration, dynamic time division, duplexing, etc. Good. Then fourth important thing is about the multi-connectivity in 5G, which refers to the capability of a user device, a user equipment also called, to simultaneously connect to multiple cells or base stations within the same or different frequency bands. And what we can also do is that it supports diverse types of traffic within the same frame. So we can have ultra reliable, low latency communication, and at the same time enhance mobile broadband in a single frame. And that enhances, of course, the reliability, the performance, and the overall user experience. And then finally, very important is, of course, that it's built upon the idea of a distributed architecture, which is a fundamental design principle, and that aims to provide improved flexibility, scalability, and efficiency in all the network operations. Okay, good. But in addition to the radio, also the whole 5G architecture became softwareized. And it's also, we are not going to focus security with respect to radio aspects, but more on this 5G core architecture. And it became softwareized. It didn't become softwareized from the first step. So it's in fact 4 phases that it had to go through. And in the first phase, we have the virtualization phase, which refers to the implementation of network function virtualization. And that involves transforming traditional network functions, which were previously implemented in dedicated hardware, into software-based functions running on virtualized infrastructure. And with the main goal to increase flexibility, scalability, and efficiency of the network operation. Then we have the second phase, which is about service migration, and that refers to the process of transitioning existing services and applications from legacy infrastructure to the newly virtualized environment, the one that we have created in phase 1. And then we have phase 3 is the orchestration, which is a critical element in a virtualized environment, and it involves the automated coordination and management of various network functions and services. So this orchestration that streamlines then also the deployment, the scaling, and the management of these virtualized resources that we have from phase 1, and so optimizes the network performance and resource utilization. And then finally, the last phase before coming there, that's then the service network automation that ensures that the entire network operates seamlessly and adapts dynamically to changing demands. So automation mechanisms help then to orchestrate and optimize resources to deliver a wider range of services. So this service network automation, there are two important aspects in that. That's network slicing and the MEC, or the multi-access edge computing. And so network slicing, that is a creation, allows the creation of multiple virtualized isolated network slices within one physical network infrastructure, with the idea that every slice can be tailored to specific service requirements such as latency, high bandwidth, massive device connectivity, and so on. So, and you all know what a MEC is. MEC is with the idea that you bring computational capabilities closer to the end users such that latency is reduced. So it's the opposite of the cloud computing. Good. So just to summarize, we have 4 main pillars in this 5G architecture. That's the SDN, software-defined networking, the network function virtualization, NFV, the multi-access edge computing is MEC, and the network slicing. So, and that's also what we're going to do. We have in the next part, we will discuss security with respect to the 5G ACA, but also with respect to each of these 4 components. So one thing I also wanted to add, so you see here on the top, the right bottom of the slide. So all is the softwareized approach is all based follow the principle. And nowadays it's kind of very trendy to say SIT and DevOps. And these are 2 frameworks. SIT is continuous integration and deployment. These are practices that are commonly used in software development and deployment in order to streamline processes. And just the SIT is a development practice where developers regularly integrate their code changes into a shared repository. And every new integration that triggers also automated build and testing processes to detect and address integration errors early. So on the other hand, and you have DevOps, that's more cultural and organizational approach that promotes then the collaboration between, on the one hand, the develop team, and on the other hand, the operation team. Okay, good. So up to here, the general idea of the main points of the infrastructure. So now we go to the 5G specific security threats. So first, what I wanted to discuss are the pre-5G security aspects. So that's the security of the previous generations that are in fact also present in 4G. And so we have discussed security of 4G before when we discussed about the history. Well, here, this is in fact everything that is related to the ACA protocol, authentication and key agreement protocol. As I said, there were some issues with that in 4G that were not completely solved. We'll find them back in 5G. They are a bit harder, some of them due to the new antenna technologies, but you cannot say that the threat is gone completely, especially not for attackers, hackers with more advanced technology, because their capabilities also increase. So what are the different threats or issues that we still need to take attention for? So first of all are the mobileware attacks, which are mostly the denial of service attacks, the botnet attacks, the advanced persistent threats, and they can still pose threats to 5G networks. These attacks have typically the ambition to disrupt the services, compromise the network resources, or gain unauthorized access during a weak moment. So it's impossible to solve this type of attack solely by having a good cryptographic ACA protocol. That's really something that you have to solve with additional tricks like intrusion detection techniques, anomaly mechanisms, and so on. So, but yeah. That can happen. Another thing are the physical layer attacks. So we can still have signal jamming, interference, eavesdropping, man-in-the-middle attacks, and they remain concerns, although they will not be able to break the privacy because you don't have the keys required for that. But it can cause some inconsistencies that are not very practical. Then roaming frauds and IP hijacking attacks. So 5G already enhances these security mechanisms for roaming, but there might always be a risk of fraudulent activities due to IP hijacking. And so here again, continuous monitoring of your network traffic are essential to mitigate these threats. We can have attacks via the non-3GPP networks because, as I said before, this 5G can coexist with non-3GPP, like, for instance, Wi-Fi, WiMAX, wireless local area networks, fixed networks. And so it's possible that if an attacker is able to break into these networks, it's then interoperable with 5G, that it can then also break into your 5G network. So therefore, you need to make sure that also security measures are in place also in these non-3GPP networks. We can have a lack of perfect for what is there is shortcomings then actually from a cryptographic point of view in the 5G ACA. That's the perfect forward secrecy attack, meaning that if a hacker to find the or to retrieve the private long-term key material of either the core and the home network or the user, then it will be able to break all previous session keys and to derive, if it has stored, of course, all the data that has been sent before, to also retrieve all this data. So that's a very big issue in the current generation 5G ACA protocols, this lack of perfect forward secrecy. And then the last one, of course, is that the mechanism 5G ACA is using public key cryptography, although limited, only actually in order to protect the privacy of the identity of the user. So, and you all know that with the current generation of public key cryptography, so in this case it's elliptic curve cryptography, that once we have a quantum computer, that it will also be broken. So, and then also, you could say that the symmetric key algorithms, that the security strength is not enough, but that's easy to solve. The more problematic part is that for the hiding of the identity, where public ECC is used, elliptic curve cryptography is used, that is vulnerable for the so-called store now and encrypt later attacks. So if you want to protect the identity of your communication for the case that there will be a quantum computer, I don't know, in 5-10 years, then it would be good to update your 5G ACA protocol to such a post-quantum resistant protocol. The only problem is that it's not so straightforward to do that, because for the resistant post-quantum protocols, they might be more or less computational efficient, but the problem is that they cost a lot with respect to communication. So they have a very high bandwidth cost. So it's not that easy to simply replace them. Okay, so these are like the issues to take into account when it comes to the ACA protocol. Then next we have the software-defined network tracks, and so as you can see here at the architecture, you can also see that there are different threat vectors at different places of your architecture. So first of all, there is point one, place one, the centralized controller, which you can also see as a potential single point of attack and failure. So if your controller is compromised, then an attacker could gain control over the entire network, leading to unauthorized access, data manipulation, service disruption, and so on. So, but then we can also have attacks on, we call that the southbound interface. So that means positions 2, 5, and 6. So between the controller and the data forwarding devices. So, and they, mainly the threats there is that it becomes vulnerable for availability attacks, and because they can be blocked, integrity breaks or integrity vulnerabilities, and performance attacks. So, and then also we have attacks on the northbound interface. That means between the controller and the application plane. So if you look at the architecture, that's positions 3 and 4. Then what we have there is mainly insecure application programming interfaces that may be susceptible to attacks such as injection, spoofing, or unauthorized data access. And there can also be malicious applications with some built-in vulnerabilities. Good. Next, so at the end, second main pillar was the NFV and network function virtualization, which was the concept of transforming hardware-based network functions like a router, a switch, and so on, into software or virtual functions. And so here, the goal is again to separate the network functions from the underlying dedicated hardware such that they can run on standard hardware. So we see again the architecture, or most important architecture of this network function virtualization. And what you can see here is that the central part is this, you see here threat vector 1 is the MANO, or the management and orchestration entity. And this is again the, if you want, a single point of attack in this, in this context of NFV threats. So if you, as an attacker, are able to break in here, then you can do quite a lot. So you can do malicious misconfigurations, excessive logging, you can leak the logs, you can make sure that you do a privilege escalation such that you have access to other parts in the architecture that are not allowed. You can steal data from ephemeral storage and so on. Good. So, and besides the MANO, we have these other threat vectors. So the second part is the attacks at the virtual network functions, where here it mainly can cause interoperability issues, denial of services, attacks, software flaws. We can have virtual machine escape, virtual network function manipulation, and so on. Then we can have on number 3, attacks on the virtual machine. So these are then the virtual migration, a problem of lack of isolation, kind of have here scheduler attacks, but that also comes then in attacks on the hypervisor, where here you can do manipulation of your virtual machine. You can break the isolation. You can also exhaust, of course, the hypervisor's kind of denial of service attack, exceed the log troubleshooting failure, and so on. And then finally, we have the attacks on the physical hardware. And here it's mainly physical attacks, really, disk failure, code execution on the physical host, state manipulation, resource interference attack, input-output, or CPU, etc. Good. Then we are Now at the third pillar, multi-access edge computing, you see again the architecture with the different threat vectors. So if we go over it, first of all, we have the vulnerabilities at the level of the user equipment. User equipment can be IoT devices, mobile phones, drones, cars, etc. So here mainly it's denial of service attacks that allow disruption of the architecture, that add fake data to the network, for instance. Then we can have attacks on the communication channels. There are quite a lot of communication channels. So you see here number 2 is between the user device and base station. We have number 4 is between base stations among each other, base station and the core network. And then 7 is between, it's the internet in fact, between third-party cloud services, the core and the MAC server. So here on the communication channel, it's mostly about eavesdropping, Sybil attacks, spoofing, relay, denial of service attacks, enabling man-in-the-middle attacks, and so on. And then, of course, we have number 3, which is then the edge network, because it's the MAC. And here it's about components that are, these are the components in the edge network that launch the storage and provision the services for the MAC subscribers. So attack vectors then mainly target the virtualization technologies, such as virtual machine manipulation, virtual machine escape. Also, like we've seen before, a virtual network function, location shift, domain name system amplification, security, log troubleshooting, and so on. And then finally, we have the attacks on the core network. And so that's number 5 and 6. So here it's a bit the same as what we have in the MAC, but then one layer higher. So even here is the most critical part if this is attacked, and that can be, for instance, by insecure APIs of your application, authentication or authorization issues, again, denial of service attacks, malicious injections, and the less isolation you have, the higher the impact is, of course, on the whole network. Okay, and then finally, the last pillar is the slicing. And here, network slicing is the separation of multiple virtual networks that operate on the same physical hardware for different application services or purposes. So we can have like 4 main threats. So it's possible that there will be side channel attacks across slices due to different security protocols or policies in different slices. It's possible to have impersonation attacks against a network slice instance within an operator network. We can, of course, have denial of service attacks to other slices by exhausting network resources. And then finally, it's possible that information can be stolen from slices if you have a user equipment that is attached to several slices. So, and there is not a proper isolation between both of them. Okay, now that we've seen an overview of all the security threats, what are the general security solutions? I keep them general, and I also combine them for these 4 main pillars, so the SDN, NFV, MAC, and slicing, because basically it always comes into the same principles. So you need to have strong authentication and authorization for every single entry points or every single element entity in your network. And that can be SDN controllers, switches, NFVs, MAC slices, managers, other components. So it's very important that strict access controls are enforced based on roles and responsibilities to limit the privileges of authorized users. Then it's clear that communication should be secure, preferably end-to-end or hop by hop, and security of communication that requires that you use secure and well-established cryptographic protocols, TLS, IPsec, etc., and also which have secure cryptographic algorithms included. So because then you can prevent eavesdropping attacks and unauthorized access to sensitive information. Another important point is isolation and network segmentation. So if you want to reduce the attack surface, you need to work with micro segmentation and isolate critical assets in order to limit the movement of an attack in your network. Fourth thing is, of course, do regular software updates and patches. So that's clear that you need to keep the devices up to date with the latest security patches, and that software need to be regularly updated to address vulnerabilities that are known in the meantime and to reduce the risk of exploitation. This also includes like proper security monitoring and logging. So to implement real-time monitoring of traffic and events. So nowadays you have a lot of AI tools that allow you to do that. The logging mechanisms, they are kind of essential in order to analyze data and signs of malicious activity. And so you can set up alerts for suspicious behavior to enable incident response. And these are the so-called IDPS, intrusion detection, and IDPS is the intrusion prevention attack systems. What else we can say is that, of course, security audits, it's something that is, if your company is complying to regulations like ISO 27001, they also enforce you to install regularly security audits, so they can also help you to overcome or to detect attacks. Another thing is like what they often call supply chain security, is to ensure that the vendor with who you work has appropriate security assurance. So that's, for instance, if you want to be compliant with NIS2, it's one of the very important criteria that you have to address. And then also in each and every security policy, education and training is seen as a very crucial security feature to take into account. Okay, good. So I think we are here at the end of the call of the presentation. I can end with some conclusions or key takeaways. So although maybe first to say that this network softwareization that we have shown to come to the 5G really core architecture, that brought many advantages like fast deployments, update of security mechanisms, centralized security controls, and granular policy management, there are still several new security issues that require additional care. We have the fact that 5G has open architecture, and especially now, since also support approaches like ORAN, where we have multiple vendors and third parties to contribute to network components like radio units, distributed units. This openness that increases the attack surface, and so introduces also many more points for malicious actors, including supply chain attacks, where we have compromised hardware of software that can come from untrusted vendors and that can be exploited. So the fact is also that when we shift to this softwareized 5G, and then it also requires operators and developers to have deep expertise in securing virtualized environments, and that is completely or significantly different from traditional hardware-centric networks. And so it's this lack of widespread know-how among staff that can sometimes lead to misconfigurations, human errors, unpatched vulnerabilities, and sometimes also inadequate security policies. Third thing is that we can have the software-defined systems in 5G, such as virtualized baseband units or control planes. They are more susceptible to hacking because they rely on code that can be reverse engineered, exploited via zero-day vulnerabilities, or attacked through malware. So this hardware and then what we had before, these hardware-based systems, they often had physical temper resistant, and they were much harder to modify remotely. So that's something to take into account. What we also have is that this virtualization that eliminates traditional network perimeters. So the physical firewalls that we had before, it relies now on software-defined boundaries, which are less tangible and harder to secure. So without physical security, like for instance, locked server rooms, these virtualized elements are vulnerable to remote attacks, especially if hosted in multi-tenant cloud environments. And then finally, we have a softwareization approach that enables a rapid deployment of virtualized network functions to meet the demands for all types of traffic. But the fact is that this speed can often also bypass thorough security testing, and so potentially introduce vulnerabilities that attackers can exploit before patches are available. So, and as a consequence, to conclude, what we have explained in this presentation is in fact a link between security threats and architectures that are related to these new approaches and the SDN and NFV, MAC, and slices. And it's important to take into account that proper protection of each of these components is required. And you know, what they say is that security is as strong as the weakest link. So now we have here much more links included. So it's also each and every link that needs proper protection. So what we didn't address in here, but there are many new technologies besides the standard approaches of access control monitoring that will enhance the security management. That includes distributed ledger technology, super interesting in the context of 5G, 6G. Artificial intelligence, machine learning, also super interesting. We'll see more about that. We have physical layers protection techniques. It's a domain in itself, and I touched a bit upon the quantum technology, but here it goes much more further with quantum key distribution and so on. And also, I want to just end with the fact that privacy is also an important challenge to take into account. It's a presentation on its own, what I didn't do here. So this was really just a basic focus on security with respect to 5G architecture. So that was the presentation. So thank you very much for listening. And if you have any questions, then I'm very happy to address your questions.
Thank you very much, Professor Anne. I have here some questions that some students have sent me. How do the security mechanisms in 5G differ fundamentally from those envisioned for 6G?
Well, the thing is that the difference between 5G and 6G is that 6G is much more relying on artificial intelligence and machine learning mechanisms. So 5G is putting the foundation, but really the automation, not only automation with respect to orchestration and so on, but also with respect to security management is really something that will be addressed in the next generation. And second important part is that post-quantum technology is something that will very likely be included in 6G, which is currently not at all present in 5G. So these are, like, I think, two main aspects that differ between 5G and 6G.
Thank you. Is here another question? What role do hardware components play in ensuring end-to-end security in future wireless systems?
Yeah, so hardware security, then mostly it's related to trusted execution environments, secure hardware, tamper-proof storage, and so on. So, of course, this will be very important. It's always been very important. So, and because you don't want an attacker to be able to have access to critical components, not only of the device of your IP, but also on the keys that are stored in there. So hardware security is a very important domain. And that's not limited to 6G. Of course, this is in 5G or even the previous generations. It's super important.
Okay, thank you. I think here is another question. Who sent me this? Albert. How can emerging technologies such as artificial intelligence, blockchain, quantum computing, and trust execution environments especially contribute to overcoming the key challenges of security orchestration in 5G and V5G networks?
Yes, so distributed ledger technology. So why can they use this first of all to ensure transparency for the management of the network, auditability, the logging, automation. These things can all be put on the distributed ledger. It's a decentralized approach, which is also following the idea of 5G and 6G. So from that point of view, it has certainly an added value. There's lots of literature on that. It's like the advantages of DLT in 5G or in 6G. It's super interesting. If you're interested, I can refer you to that. So artificial intelligence and machine learning, that's on two sides. On the one hand, we can apply artificial intelligence and machine learning to improve the security, and that's meaning then to improve your tools for intrusion detection and prevention, anomaly detection, and so on. But on the other hand, it's also challenging to make sure that your artificial intelligence is secure on itself. So meaning that it uses that the data on which it's based is not fake data, that you have your protection against all these type adversarial AI attacks, etc. So that's a double sword, they call it. So AI for security, but security for AI. So yeah, physical layer protection and the trusted execution environments are important to make sure that if your attacker somehow has physical access to devices, because we work in a decentralized environment, it's possible to have more entry points, physical entry points also, to protect you against that. And then, yeah, quantum is clear. So yeah, to make sure that as I explained to you then for this 5G ACA protocol that we have now, it's relying on traditional cryptographic primitives which are not resistant to quantum computers. So in order to overcome your protection, you have to find a solution in that. Yeah, that's it.
Thank you so much.
Hola. If it's okay, can I jump in with one question?
Yeah. Okay. Here is another question. Go ahead.
Okay. So because I want to utilize this platform as well, because it's very international meeting. As you can see, we're between Europe and Latin America. So there may be a lot of people, especially from your side, interested in the research that is ongoing in the European countries. And as you know, we do have 5G deployed in most countries. The 6G is what we are involved in. So there are a lot of people that will be giving the presentations that are currently involved in defining the 6G throughout a lot of different European projects. So we have been, Anne has covered a lot of, well, I mean, from the beginning to the history of the generations until now. And then there's beyond this. She has talked about the security challenges, but challenges in general. So I just want to throw in here that in Europe, there's still a lot of open research happening, and there's still a lot of opportunities. So we look into, things like in the physical layer, we look into reflective intelligence services. There were some questions about TEEs. So we do have companies, for example, like NEC, that is looking into the trusted execution environments. People do work in let's say, the architecture itself. So there's a lot of work going on in zero touch management. And as you know, we have seen already the shift from 4G to 5G, where it wasn't only a shift in terms of a better throughput and a better speed, essentially. We also have seen the change in the whole paradigm, like distribution of the network, multi-vendor environments. And we also see this 5G to 6G. It's not just 5G on steroids, meaning 5G with AI capabilities, but it's also either further this organization of the network. So coming to the point, there is a lot of research in 5G and 6G happening in Europe and a lot of opportunities. And in your group, what is it that you are focusing on? Because perhaps we can build also some connections with the attendees. Like, what's your main focus in your group?
Yeah, so the main focus that we do is on the authentication and key agreement protocols. So in fact, on the cryptographic security protocols that are there between the different components. That's our expertise. Also, we worked on distributed ledger technologies because it's closely related to the security protocols. That also involves quantum. I mean, developing the protocols nowadays is quantum resistance is quite hot to include in your protocols. And then also when it comes to physical layer protection, it's things that we look at, but mainly from the point of integration into our protocols, not like designing our own trusted execution environments, but really using it as a starting point for defining our protocols. So, but we are not like specialists in this AI based techniques, like what I know that other groups are, working really hard on it.
Yes, perfect. So, the post quantum crypto, all the research groups that look into different lightweight protocols. Also, this is still a very hot topic in research and industry. And I think I mentioned just now the lightweight. Everyone is now looking into energy efficiency aspect of the solutions that are being developed for 5G or beyond 5G. And in fact, any proposal for the project that you put in now in this current environment has to be covering some aspect of energy efficiency and sustainability also. So if there is any researchers interested in that, I do recommend linking up with some EU partners that may have some opportunities to work together. Just taking this opportunity to link up the presenters also with everyone else that's here. Back to you, Paola.
Yeah, thank you so much. Now, I don't know if we have Bart more time for more questions, or we continue with Chamita.